Welcome to video clip 3.5, in which we provide an informal PetriNet primer, and this is a bonus video. So, PetriNets are graphs that capture the behavior of systems. It's a formal representation of concurrent system and widely used for the analysis of dynamic systems. The PetriNets have been devised by Carl Adam Petri in his dissertation from 1962. They provide a theory of the communication of systems, and since then, of course, many extensions and many variants have been developed since. And PetriNets are used widely by the academic BPM community to formally analyze process models and also for many other purposes. Here we see a picture of Professor Petri receiving an award. So the person in the middle is Professor Petri receiving an award in the Netherlands. All right, so a PetriNet is a directed graph comprised of places, transitions, and directed arcs between these. The graph is bipartite, meaning that arcs are only allowed between nodes of different types. So an arc can either go from a transition to a place or from a place to a transition. Arcs between two transitions and arcs between two places are forbidden. All right, let's introduce some terminology. And that is, here we see a PetriNet. I should say a few words about the PetriNet. So the places are represented as circles. The transitions are represented as rectangles. And the relationship, the arcs, or the flow relation is represented by the arrows here. And we see the graph is bipartite, so there are only edges from places to transitions, or this one, place to transition, place to transition, place to transition, or from a transition to a place. There are no other arcs here, so the graph is bipartite indeed. We need to introduce a terminology of an input place and an output place. So the output, or first of all, let's say P1 is the input place for T1, so T1 is a transition 1, and the set of all places that have errors that come into this transition is the set of input places. So P1 is the input place of T1. And looking at output, and of course, what else do we have? P2 is an input place of T2. P3 is the input place of T3. P5 has two input places, namely P5 and P6. So that's the concept of an input place. Concept of an output place is the respective concept. So P3 and P4 are output places of T2. So these two are output places of T2, and P7 is output place of T5, and P2 is output place of T1, and so forth. So we introduce a terminology that you know what an input place, or the set of input places of a transition, and the set of output places of a transition is. The behavior of a system is represented by a token play in the PetriNet. And a token is represented by this black dot, and tokens can only reside on places. So here you see the token, one token on place P1. And there are no other tokens in the net at this point in time. In general, each place may carry a number of tokens. There are different kinds of PetriNets with different constraints regarding this, but the PetriNets we use, each place may carry any number of tokens. The state of a PetriNet is defined by the distribution of tokens over the places of the net. That's the state. So often the state is might be in an initial state. The state of a PetriNet might be initial, and here we have this situation, and briefly talk about the sample PetriNet representing one process instance. So here we have a variant of the order process in which The activities in the process model are represented as transitions in the net, and the flow is represented by the arcs and by the places. All right, so here we have the state of the Petri net that is in place P1, which means only there's one token in place P1. So we use these brackets to indicate which tokens have which places have actually tokens on them. And in our examples, we just have one token at most on each place. Therefore, we can just use the name of the place to indicate that there's one token on this place. A Petri net changes its state by firing of a transition. So transition T can fire if it is enabled. There's a concept of enablement, which is not too different from the ready state of the activities. So once a transition is enabled, it can fire, similar to an activity that is ready, can be executed. So a transition T can fire if it is enabled, and T is enabled if each input place carries at least one token. Each input place of that transition has at least one token. It is enabled and it can fire. On firing of a transition T, it consumes one token from each input place and produces one token on each of its output places. So let's walk through these, let's apply these state changes here. So let's assume the initial state of the process is P1. So the process model is in state P1. Which transitions are enabled? Well, just one transition is enabled, which is transition T1, because all input places have at least one token. So this transition is now enabled. It can fire. So if it fires, what happens? Well, from each, in an atomic step, so I cannot do this atomic step, I need to do that step by step, but it is an indivisible atomic step, the firing of a transition. What happens is that one token is removed from an input place and one token is put on each of its output places, which is just one in this case. So that's the firing of transition T1. Okay, so let's erase that now. So how does the process continue? Well, there's another transition that is enabled at this point in time, which is T2. T2 also, in an atomic step, removes a token from P2 and puts a token on P3 and P4, because all output places will receive one additional token. So I erase the token here. That's also done in an atomic step, in which I'm not very good in. So that's the state of the process of the Petri net, the process after execution of the triggering or after the firing of T2. Then we have a concurrent branch here. We see also concurrency, that send books and update inventory can be executed in any order. So assume that first send books is performed, so the upper transition fires, bring the token here. So which transitions are enabled at this point in time? Well, is it T5? No, it's not T5, because there's one input place without a token. So P6 does not have a token, therefore T5 is not enabled, but T4 is enabled. So T4 can fire, removing a token here, putting a token here. Now T5 is enabled. T5 can fire. So these two need to be erased, and on each output place one token is produced. So we have here the execution, or the putting T5 puts a token on place P7, thereby completing the process. So I was discussing the behavior of a Petri net in terms of, well, the concept that we use in Petri nets. But at the same time, I think you also recognize that I was describing a process execution, trace of the process. So first order is received, then the order is processed, then we have the concurrency, and then afterwards we have the join. So here we can even say that the Petri net realizes an end split and then also an end join behavior by the rules that we just learned from Petri nets. There are also ways to realize an XOR split in Petri nets. That is also possible. A very easy way. We'll come to that soon. Okay. Now the question is how we can discuss what are the states that are reachable that a Petri net can achieve. What are the states that are reachable? And in order to do that, we'll like to introduce a reachability graph, also in a very informal way. A reachability graph is a graph in which the nodes are states. And state transitions state transitions are represented by an arc and the follow-up state that is then achieved. So let's see if we can design the reachability graph of this process model, or this Petri net, I should say. It starts the first state, or currently the Petri net is in state P1. State P1 is the first state. Then by firing, and we can associate or can we annotate the firing of the transition to the edge in this reachability graph. So more correctly, I should say P1 in brackets, because we introduced the structure, the state as being the name of the transitions in brackets, but due to better readability, I will not use these brackets any further here in this example. All right, so T1 can fire. What is the resulting state? The resulting state will be state P2. One token in P2 and no other token in the net. Then T2 can fire. T2 is enabled. T2 can fire. And then a state P3, P4 is reached. P3, P4 is reached. In P3, P4, we have concurrency because two different things can happen. Either T3 can fire, or T4 can fire. Both can fire because tokens are on P3. One token is on P3 and one token is on P4. After T3 has fired, what happens? The token goes from P3 to P5, resulting in P5, P4. If, on the other hand, in state P3, P4, T4 fires, we end up in state P3, P6. P3, P6. All right, and then, we after P3 has fired, T3 has fired, T4 can fire, and that brings us to T4 can fire, P5, P6. And we also reach P5, P6 if here P3 fires. At that point, we have tokens in P5 and P6, so that T5 can fire, and we end up in P7. Yeah. That's the reachability graph of this Petri net. So it shows all states that are reachable by this Petri net, and it also tells us which transitions are used to achieve the respective state transitions. All right, that again discusses the firing of a transition, but I think I went through this in quite detail already. All right, that concludes basically our Petri net primer. I introduced Petri net in an informal way. I explained that there are states, that there are places, and that there are transitions. That's a bipartite structure on states and transitions. I discussed the structure of a Petri net and also the behavior of Petri net that is defined by the token play, and I also looked at the reachability graph.